Hello class, Professor Anderson here. Welcome to another edition of Learning Glass, Lectures on Physics. How's everybody feeling today? Yeah? I'm seeing some positive nods, that's good. Everybody getting excited for the final?
Yeah.
Getting excited to be done? Yeah. All right. So let's take a look at a few of the practice problems that we posted. And you guys chose a couple to look at. And the first one you wanted to look at is the space shuttle in orbit. And it's going to change its altitude. Okay, so what they tell us is that the space shuttle is orbiting the Earth. Here is our space shuttle. Okay, and it's going around at some particular altitude. We'll call that h1. And then it wants to increase its altitude. Okay, so it's going to end up here at a height h2 and still going around. Okay, and we need to figure out how much energy it had to burn to do that, right? You fire the thrusters on the space shuttle, it's going to move up in its altitude. How much energy is required to do that? And let's tell you a few things, okay? So the numbers that we have are the following. H1 is 250 kilometers. And in SI units, that would be 2.5 times 10 to the 5 meters. And H2 is 610 kilometers, which would be 6.1 times 10 to the 5 meters. What else do we know? We know the mass of the shuttle. That is 75,000 kilograms. So if we put that in scientific notation, it's 7.5 times 10 to the 4 kilograms. And that's about it. We're going to have to, of course, know something about the mass of the Earth and the radius of the Earth. And if you look on your info sheet, the mass of the Earth is 5.98 times 10 to the 24 kilograms. And the radius of the Earth is 6.27 times 10 to the 6 meters. Okay, so that's all the givens that we have. There's, of course, the radius of Earth, and there's some mass of the Earth. Okay, so how do we do this problem? Who's got the microphone? Chase. Perfect. Chase, how do we do this problem?
You use a energy equation for gravity.
Okay, some sort of energy equation that involves gravity. I like it. I like it a lot. Let me ask you a question. We went through this problem a little while ago, and we did the following. We calculated the work required to push this thing up against gravity. Okay, and when we did that, we got a certain answer. And it turns out that that answer did not agree with the energy equation that you're talking about. And the reason it didn't agree is the following. If you are just pushing this thing up, working against gravity, you haven't taken into account the fact that the velocity doesn't have to be as high up there, right? If the orbit is bigger, the speed of the space shuttle can be smaller. And so your kinetic energy can in fact be less. All right, so what we need to know is the energy in an orbit. Okay? Energy is, of course, 1/2 mv squared. It's moving, it has kinetic energy. But it also has gravitational potential energy, Gmm over r. Okay? This is always true, kinetic plus potential. Remember, our potential energy for gravity is negative now. But we don't really know how these two things relate. And so we need another equation to relate those two. And the other equation that we use is summing the forces for circular motion. There's only one force here, which is gravity, gmm over r squared. All of that has to equal mv squared over r. And now look what happens. If I multiply by r on both sides, and I multiply by a half on both sides, I can rewrite this as the following. 1/2 mv squared equals 1/2 gmm over r. And I saw the light. All right. That means that we can plug this in to our energy equation. Okay? And so what does this energy equation become? Well, it's 1/2 mv squared, which is now this. 1/2 gmm over r. And we're still subtracting gmm over r. And so we get a nice little final result here. It is 1/2 minus 1, and so we get negative 1/2 gmm over r. This is the energy of a circular orbit, the total energy. We started from kinetic plus potential, but we were able to write it all in terms of these gravitational constant, mass of the Earth, mass of the shuttle, distance from the center of the Earth. Okay, so this is the energy equation that Chase was just mentioning that we want to use. And now we can calculate what's the difference between these two. I'm going to have some energy here in orbit H1. I'm going to have a different energy in orbit H2. Whatever that difference is, that's how much energy I have to add to the system. All right, so let's calculate that. So we're going to say that